So let's take a look at indeterminate forms and L'Hopital's rule. Now let's say you have the limit as x approaches some value a of a function f of x over another function g of x. Let's go ahead and you evaluate this limit by using direct substitution. So you plug in a for x into both functions, so you get f of a over g of a. Now, when you plug in those values, if you get an answer of 0 over 0 or plus or minus infinity over infinity, both of these are known as indeterminate forms. And because they are indeterminate forms, you can use L'Hopital's rule. And so what L'Hopital's rule is you rewrite the limit, so the limit as x approaches a, but this time you go ahead and take the derivative of the numerator, so f prime of x, over the derivative of the denominator, g prime of x. And then you can go ahead and evaluate from there. Now keep in mind that sometimes you might only need to use L'Hopital's rule once, other times it might be more than once. So let's go ahead and find the limit. Number one, we have the limit as x approaches negative 1 of x squared minus 1 over x plus 1. So first step here, let's go ahead and use direct substitution, directly plug in negative 1 into x into the function. So we get negative 1 squared, which is 1, so we get 1 minus 1 in the numerator over negative 1 plus 1. Now 1 minus 1 is 0, negative 1 plus 1 is 0. Because it's in that indeterminate form of 0 over 0, we can go ahead and go back to the original limit and use L'Hopital's rule. Now remember, in L'Hopital's rule, we take the derivative of the numerator and the derivative of the denominator. So the first derivative of the numerator, derivative of x squared minus 1, is just going to be 2x. And then derivative of x plus 1 is just going to be 1. So 2x over 1 is going to give us 2x. And now we can go ahead and rewrite the limit. So we rewrite it as the limit as x approaches negative 1 of 2x. In this case, we can use direct substitution. So we plug in negative 1 for x, and we get 2 times negative 1, which is negative 2. So that's the limit. Now for number 2, we have the limit as x approaches infinity of the natural log of x over x. So if we go ahead and plug in infinity for x using direct substitution, we get the natural log of infinity over infinity. Now the natural log of infinity, if we took a look at the graph of the natural log of x, it might look something like this. So as the x values increase without bound all the way to infinity, the y values will also go to positive infinity. So ln of infinity is basically infinity. The denominator is also infinity, so because we have it in this indeterminate form, we can go ahead and use L'Hopital's rule. So if I go ahead and go back to the original limit, once again we're going to take the derivative of the numerator and the derivative of the denominator. So derivative of a natural log of x is just going to be 1 over x, and the derivative of x is just 1. 1 over x over 1 is just 1 over x. So now we can go ahead and rewrite the limit as x approaches infinity of 1 over x. If I go ahead and use direct substitution, we get 1 over infinity, and 1 divided by a very large number gets closer and closer to 0. So we're basically, the limit is going to be 0. Now for number 3, we have the limit as x approaches 0 of e to the x minus 1 minus x over x squared. Once again, when we use direct substitution here, plug in 0 for x, e to the 0 is 1, so we have 1 minus 1 minus 0 over 0 squared, which is 0. 1 minus 1 is 0, 0 minus 0 is 0. So we do get 0 over 0. Because we have an indeterminate form, we go back to the limit and use L'Hopital's rule. So now we take the derivative of the numerator. Derivative of e to the x is e to the x. Derivative of negative 1 is 0, and derivative of negative x is negative 1. Over derivative of x squared, which is 2x. So now if I go ahead and rewrite the limit as x approaches 0 of e to the x minus 1 over 2x. If I use direct substitution here, we get e to the 0, which is 1. 1 minus 1 is 0. So 0 on the top, and then 2 times 0 is also 0. Now we do have an indeterminate form once again, but the good thing is we can use L'Hopital's rule again if it's still indeterminate. So I'll go once again back to our limit here, and we can use L'Hopital's rule. So we take the derivative of e to the x minus 1, which is just e to the x, over derivative of 2x is 2. So now rewriting the limit, we have the limit as x approaches 0 of e to the x over 2. So now when I plug in 0 for x, use direct substitution, e to the 0 is 1, so we get 1/2 as our limit. Now for number 4, we have the limit as x approaches 0 of 1 minus cosine x over x squared. If I use direct substitution, cosine x, or cosine of 0 is 1, 1 minus 1 is 0, over 0 squared, which is 0, so we can use once again L'Hopital's rule. Now I'm going to go ahead and take the derivative of the numerator, so derivative of 1 minus cosine x, so derivative of negative cosine x is going to be sine x, positive sine x, over derivative of x squared, which is 2x. When I go ahead and rewrite the limit, we have the limit as x approaches 0 of sine x over 2x. Realize that when I plug in 0 for x, we get sine of 0, which is 0, over 2 times 0, which is 0. So we have to use L'Hopital's rule one more time. Now I'll go ahead and derive the numerator. So the derivative of sine x is going to be cosine x. And the derivative of 2x is 2. So now rewriting the limit as x approaches 0 of cosine x over 2. Using direct substitution, plugging in 0 for x, cosine of 0 is 1. So we get our answer of 1/2. Now for number 5, we have the limit as x approaches infinity of x cubed times e to the negative x squared. So very first thing, once again, direct substitution. If I plug in infinity for x, infinity cubed is infinity, and then we have times e to the negative infinity squared. So infinity squared is still infinity, negative 1 times infinity is negative infinity, so we have e to the negative infinity. Now I can rewrite e to the negative infinity as 1 over e to the infinity. E to the infinity is basically infinity, so we have infinity times 1 over infinity. Now 1 over a very large number, or 1 over infinity, is basically 0, so we have infinity times 0. Now this is not an indeterminate form because it's not 0 over 0 or infinity over infinity. So what we have to do here is go back to the limit, the original limit, and sort of change what we have so that we can get it in that indeterminate form. So the very first thing is, if there's a negative exponent, it's probably a good chance that you have to bring it to the denominator. So I'm going to rewrite the limit as x approaches infinity of x cubed over, I'll bring that negative exponent down, so e to the x squared. So now when I use direct substitution, plugging in infinity for x, on the top we have infinity cubed, which is infinity, over e to the infinity squared. Infinity squared is infinity, and e to the infinity, if I go ahead and write that down, e to the infinity is basically infinity, so we have infinity over infinity. Now we have that indeterminate form. Now we can go ahead and use L'Hopital's rule. So if I go ahead and erase this half here, so the derivative of the numerator here, derivative of x cubed, is going to be 3x squared. And then we have over the derivative of e to the x squared. Now remember, the derivative of e raised to some function u is going to be e to the u times u prime, basically a chain rule. So derivative of e to the x squared is going to be e to the x squared times the derivative of that inside function. Derivative of x squared is going to be 2x. So realize I can simplify this a little bit. One of the x's will cancel. So then we're left with 3x over e to the x squared. So now rewriting the limit, we have the limit as x approaches infinity of 3x over e to the x squared. When I use direct substitution, we get 3 times infinity, which is infinity, over e to the infinity, which is basically still going to be infinity over infinity. So we have to go back to this limit. We got to use L'Hopital's rule once again. So the derivative of 3x is going to be 3 over derivative of e to the x squared, once again, is e to the x squared times 2x. So now when I go ahead and rewrite the limit as x approaches infinity of 3 over 2x e to the x squared, using direct substitution, we have 3 over 2 times infinity is infinity, times e to the infinity squared, which is basically still going to be infinity. Infinity times infinity is infinity, so we do have 3 over infinity. Now 3 divided by a very large number, like infinity, is basically going to get 0. We're going to get closer and closer to 0. So that is going to be our final answer for the limit.